All right, we're going to start the second half of day one and start to build off what I think Chad introduced us to at the start and start focusing on more specific applications and technologies. We have Yuan Yu from Sandia National Laboratories. He got his PhD in 2005 from Princeton, and he's a PI lead researcher at Sandia now, doing lots of things, including electric field sensing, clocks, and a lot of the things he's going to explain to us today. So let's give him a round of applause. Here you go.
All right, thank you, everyone. Can you hear me? Yeah, I'm not sure the microphone is working or not. Okay, I'm Yuan Yu Jau from Sandia National Labs. And thanks for giving me this opportunity to talk about some stuff I've been doing, but mainly what I'm going to focus is on a different perspective. More focusing on the application side, try to make the quantum sensors to be deployable, meaning like not just in the lab environment, but outside the lab space. And for that, I'll be mainly talking about the vapor cell-based technology. So some topics I'm going to talk about will have some overlap with what Chad talked about this morning, but I hope I can give you some more context and some complementary information about that. Okay, so I will start with the fundamentals of atomic metrology. The main focus will be on using atoms inside the glass cell or the vapor cell. But with that, we have to talk about what atom can do. So there are 5 major categories for atom to be used for sensing application. And most of you may probably already know, one is time, like atomic clock, magnetic field, atomic attometer, electric field, atomic electrometer, and acceleration rotation, atomic interferometry for atomic accelerometer, and gyroscope. The reason we like to use atoms, one very important reason is, basically we believe atoms are indistinguishable, meaning they are basically the same, regardless of where you find them, on this side of the Earth or the other side of the Earth, or maybe even on the other corner of the galaxy. And this is what we believe. So if atoms are all the same, that means we can use them to make calibration-free or traceable standard sensors. Because they are only defined by the fundamental constants. So we'll be able to achieve the best metrology accuracy because in principle, if they only rely on the fundamental constants, then we don't need to calibrate that. But of course, the fundamental constant may be changing over time, which we don't know. But at least currently, we think they are pretty much like constants. And then the second thing is atoms. They contain lots of internal quantum states. So even the single atom is a very versatile quantum system. You can find infinite number of quantum states inside an atom, and you use different quantum states, you can do different kind of metrology, and this quantum limited measurement give you the lowest uncertainty that not only give us, the best accuracy, but also the precision or the sensitivity. And a few illustrative figures on the bottom of the slide just to show what I mean by measuring time, right? So the atomic clock, we use the transition, which is insensitive to anything. Basically, that's what we like to use because the energy difference of the pair of the energy state, if it is sensitive to any physical quantities, then we can use that to make a precision timing source. And currently, we know cesium atom is still being used to define time. But on the other hand, we also know these days the best clock is actually based on the optical transition of the atom instead of the microwave transition of the atom. So currently, we talk about conventionally the 2 typical examples. The microwave clock is based on cesium atom. The optical clock is based on other atoms, for example, strontium or ytterbium or some others. And atomic magnetometer, we use energy states which are sensitive to magnetic field. So by applying the magnetic field, you will see the energy level shifted, and then we can measure the shift of the state to determine the magnetic field. Electric field, similar concept. We try to utilize internal atomic state, which is sensitive to electric field. And then we have other two examples for acceleration, using the state, which can see the sensitivity to the acceleration, and also using the state, which can see the sensitivity to rotation. So currently, these are still the 5 major categories for atomic metrology. Okay, the basic unit of atomic quantum sensing and computing. Chad kind of already told about this morning. What we have to do, usually we have to find at least 2 discrete quantum states from the system. It can be from single atom, or it can be from an ensemble of atoms, depending on how you encode or define the 2 states you would like to take advantage of. And this 2-level entity is usually called a spin, and most of the time it's actually a pseudo spin, meaning you don't really see a physical angular momentum in the real space. It's just the 2-level system can be mapped to a Bloch sphere, and that's a pseudo spin. Or these days, a fancy term is qubit, because you can use a 2-level system as a computation unit for quantum computing. So each one of the 2 states, has its own phase, and this phase depends on time or position. So it's depending on the 4-dimensional space-time. And the reason it does that is because we know each quantum state can have different energy, and if it has different energy, it evolves the phase change in time. If it has a different angular momentum, if it has different momentum, and then it change the phase in space. So 2 level is the basic unit, because in order to determine the state, the phase difference, you have to use one and compare with the other. You cannot determine what the phase is just with single quantum state. That's not doable. So that's why we say this is the basic unit. But it's not necessary to be 2. You can have more than 2, as long as you can figure out how the phase of each state evolve in time or in space. So quantum sensing 101 is we try to measure the phase difference between the 2 states due to the interaction with a specific physical quantity. And that can be time, magnetic field, electric field, acceleration, and rotation. But regardless of what physical quantity we're talking about, it's all about measuring the phase or the frequency. All right? So if we have enough atoms, you can actually determine this phase quantity very precisely. And that's how we're going to achieve very precise atomic metrology. And just a quick review again. Chad talked about this morning. If you have a 2-level system, and then we can map this 2-level system to a Bloch sphere, and this is what we usually call the pseudo spin. It's just a vector pointing, on this 4-pi surface of the Bloch sphere. And usually this vector can be manipulated by the Pauli matrices, and the Pauli matrix is actually just the generator of the SU2 group. And this can have a very good mapping to the actual spin operators. If you have more than 1 spin, you can just add all them together, and you see the ensemble behavior still follow the same single spin, commutation relation. But of course, it can be more complicated if we're talking about the non-classical state of the ensemble spin, which I'll talk about later. Okay. And the next thing I would like to point out is the measurement. So usually for the measurement, we talk about the observable of the quantum system. Observable is more like a classical, usually it's a classical thing, a classical physical quantity you would like to measure. For example, spin, it can be the real spin, the momentum, or the position, or different kind of classical quantities. And when we have the observable based on this Copenhagen interpretation, we know a quantum state give you some kind of probability. If you try to measure a specific observable, you get the probability of getting that value. It's not the absolute number, like it means it has uncertainty. So whenever you measure it comes with uncertainty, and that uncertainty actually limits our measurement precision, right? And then the second thing is the von Neumann postulate of reduction. Simply saying like, okay, if you have a quantum state with with some kind of probability population, when you measure that, and then it will just collapse into the eigenstate of your measurement. So measurement can be treated like a Hamiltonian, interaction Hamiltonian, and that interaction Hamiltonian, when you measure it, it actually dominates the entire Hamiltonian, and the eigenstate of that measurement in Hamiltonian will give you this collapse into those eigenstates. So it depends on the initial probability or the amplitude of the original superposition state, and when we measure it, it will collapse into the eigenstate. But single measurement will just give you one result, but you cannot really tell, what the real amplitude is between the two associated states. So you'll perform this multiple times until you get enough statistics, right? And then you can finally determine, oh yeah, so it's about 1/3 on the top and the 2/3 on the bottom. And this is unfortunately, that's just the case for quantum measurement. You have to perform multiple times if you only have one particle. But if you do have multiple particles at once and you just measure them all, and you will naturally just get the average result. So you can tell, for example, I can measure like a million atoms at once, and you can likely pretty much tell, okay, I got 1/3 on the top and 2/3 on the bottom, because you have enough statistics already. The uncertainty, Chaz also talked about this morning. It follows this uncertainty principle, and it can be derived, from the commutative relation. And so as long as we have some kind of canonical variable, so in the phase space, you can always construct the phase space, and then the two independent variables, if they follow this commutation relation, and this is the rule you will have. And later we will talk about, yes, we can squeeze, one variable and then increase the uncertainty of the other, and that can give us some advantage in terms of measurement. In the spin system, since we always talk about the two-level system most of the time here, a two-level system can be mapped to a pseudo-spin system. So we can always use the Pauli matrices to generate like spin operators, and the spin operator actually follow this commutative relation, and if we know what the uncertainty looks like for the two orthogonal directions. So for the spin ensemble, we know the coherent state, which is kind of the classical result. It'll give you like equal uncertainty along the two orthogonal direction in the spin space, and this just kind of like the classical thing. If you look at the uncertainty as a function of the number of particles, it's scaled with the square root of n, and n is the number of particles. So far, this has been pretty much, I mean, we do have some quantum portion of that, but if you look at the statistical behavior, it's pretty classical-like. Okay, so we talk about the measurement of phase. The uncertainty is what's limiting us in terms of measurement precision, right? And so I use this small delta phi to denote the uncertainty of the phase measurement, and that can be written like the deviation of whatever spin projection quantity like Sx or Sy, and divide by the amplitude of the spin, which is Sd. And you just do the simple math, considering it's a coherent coherent state, superposition state, and then you have the uncertainty followed is equal to 1 over square root n. And this is the so-called standard quantum limit. It's basically just a classical counting statistics. And then we know the SNR is what. So if we measure the phase difference or the change in phase is big delta phi and over small delta phi, and that's the SNR, right? Because this is the signal, and this is basically the uncertainty or the noise. And it's equal to square root of n, because just follow the math. And again, the phase is affected by whatever physical quantity we are interested. You can say, okay, this phase is a function of Q, and Q is a physical quantity of our interest. And once we're able to measure the phase, we just do the inverse function, we can calculate what the Q is. So it's pretty straightforward in terms of measurement. And for the 5 major categories I mentioned previously, you can kind of see the physical quantity we care about is time. And for a two-level system with energy difference equal to h bar omega non, and multiplied by the time difference, then we get the phase difference. So phase difference is affected by the energy of the state, of the difference of the energy of the states. For magnetometry, again, we know the phase is affected by the magnetic field. We have this gyromagnetic ratio, gamma, times magnetic field strength, and times time. And that's the amount of phase we can accumulate in the atomic system over delta t, this time span. Accelerometer, actually, okay, so far I just simply pointed out, how we make the connection between the phase we like to measure and the specific physical quantity, what the specific physical quantity is. But the real implementation of the measurement of the experiment, I haven't talked about that, but I can talk about that later. But just now, just to see, the phase is only determined by some numbers and then the time. For accelerometry, it's in terms of the phase accumulation is proportional to some constant. This A is actually the acceleration. And the effective k vector, this is actually the wave number of the 2 laser beams we introduced for this light pulse assisted atom interferometry. But the phase is actually proportional to time squared. And that's simply, when we talk about the displacement or the movement in distance with the acceleration A, is proportional to t squared. So that's how we get the phase there. Similarly, for the gyroscope, it's actually pretty straightforward. The phase is simply just the angle between the atomic spin and the probing direction. So if the thing is rotating, and the reference frame, the lab frame, and the frame for the spin is getting, there are different frames. And so if the thing's rotating, we'll see the angle between the probing direction and the spin direction is getting changed. And by measuring this change, we know how much angle is getting rotated. For electric field, we actually take advantage of atomic rebirth state. And we can also see it's determined by some constant. For example, the polarizability, the bias electric field, and the electric field and time. So basically what we are going to do is just to measure phase. But how we measure phase, it depends on what kind of physical quantity we are interested in, and then we know how we can implement the measurement and what atomic internal quantum state we would like to utilize. Okay, then this is a quick overview. Why we say atomic metrology is the best, because it does deliver the best measurement performance. So for example, atomic clocks. These days, I mentioned the best atomic clock is the optical lattice clock. Currently, they can get precision down to 10 to minus 20 with accuracy smaller than 10 to minus 18. This number is really great. What it means, if you're considering the gravitational rate shift on the Earth, 10 to the minus 20 means you can see the time dilation or time difference if you just lift your clock by 100 micron. That's really awesome. And of course, this means like from 10 to the minus 18 to 10 to the minus 20, you have to integrate down by about 10,000 seconds. So you also need to make sure you can maintain the stability for over 10,000 seconds. But 100 micron over 10,000 seconds is really not a big deal. And even though we say, okay, I don't want to wait that long, just 1 second, 10 to the minus 18, that can already give you like 1 centimeter sensitivity for the gravitational ratio. Just lift or change the height of your clock by 1 centimeter, you'll see the time difference there. For magnetometry, 10 to the minus 16 Tesla per square root hertz. The Earth's field is half Gauss, so it's about 50 microtesla. 10 to the minus 16, 50 microtesla, so it's roughly like somewhere between 10 to the minus 4 and 10 to the minus 5, right? So this is like more than 10 billion times, smaller than the Earth's field. This is also the best number. I mean, no other existing technology can give you this kind of precision or sensitivity. Accelerometer, 10 to the minus 11 G, and we know, the acceleration on the surface of the Earth is 1 G, right? So this is 10 to the minus 11. So that's the best number. Other things like rotation, 10 to the minus 6 degree per square root hour, because rotation is something like you will see this random walk thing. The uncertainty of angle accumulates over time. But this is actually the pretty good number if you compare with other technology like a laser gyro. It cannot give you this. Electric field sensing. I'll talk more about this later. I've been focusing on what I call the quasi-DC, so the low frequency band electric field detection. And this is also the best number, 10 to the minus 6 volt per centimeter per square root hertz. Okay, so all this is basically achieved by what I call the quantum 1.0. Like Chad talked about the definition of quantum 1.0 and quantum 2.0. I have a really different definition, but I'll explain what my definition is. Anyway, here, this is what I call about the quantum 1.0. Okay. In general, atomic metrology gives you better performance for low frequency detection and low data rate. That's the thing. I'll explain later. Okay, then let's talk about the Heisenberg uncertainty principle again. We know this is how we define the deviation, right? So we have, the expectation value of the observable square minus the mean value of the observable, and then square, right? And then we take the difference of that, and then it follows this commutation relation. There's two canonical variable. The product of them must be equal or greater than half of this commutation value. And so we can quickly apply this math for XMP, precision and momentum, right? And then we know, okay, this is the famous, right, space momentum uncertainty principle. And the same thing, we can apply to the spin operators. We talk about any two-level system can be treated like a spin, a pseudo-spin. And then it does follow this uncertainty principle relation. If you look at the phase space, the simple harmonic oscillator, this is equivalent to photon. If you look at the amplitude and the phase, and also here is a position and momentum, and in the spin domain, we can see it's equal to Sx and Sy. The ground state is just a Gaussian distribution. If you get excited, mean like we have some amplitude. The classical coherent state is like we have this uncertainty, which is the same as the ground state, but it's rotating, in this phase space over time, and the rotation speed is just equal to the frequency we talk about for the simple harmonic oscillator, or for photons, that's the photon frequency. For spin, that really depends on what determine the energy level spacing of the two-level system. So in the ground state, it's also kind of just stop there. So this is a bit different. For spin system, we talk about the Bloch sphere. When we see something like this, that means the spin is pointing along the z direction. So we only make the projection along on the xy plane. And the equivalent ground state is like the spin is aligned to z. And so the value along x and y is 0. and the uncertainty is the same as the simple harmonic oscillator. You also find something like the Gaussian distribution there. If we tip the spin a little bit off from the z-axis, and it stops precessing, and this precession frequency is equal to the energy difference of the two-level system divided by h bar or h, depends on how you define the frequency. And you will find a very nice connection between these two systems, and because the math is basically just the same. Okay, so the spin coherent state, just quickly go through this. This is the dimensionless unit, so we don't see h bar or mass or whatever there. Just talking about the later operators. We have a creation, annihilation operator. We can use this to define x operator, position operator, and momentum operator for a simple harmonic oscillator. Conventionally, we know this is quadratic potential or parabolic curve. The ground state is like that. It's not moving anywhere. We get that distribution, like along, under the phase plane in the phase space, and this is like a Gaussian distribution. Typically, we say, okay, we can find something we call the displacement operator, and usually, in the test book, they just say, well, you introduce this, apply to the ground state or the vacuum, and then you will find the coherent state with an amplitude equal to alpha. But it's really coming from the classical interaction. If you have like a force applied to your oscillator, you're going to displace, just thinking about the classical picture, you're going to displace that mass from the original equilibrium position on this connect to the spring, and then once we do that, we can see how it evolves in time using the unitary operator, which can be easily calculated using the interaction Hamiltonian. And you just do some math, you'll find, oh, this is equivalent to the displacement operator. And that's how we actually, make a simple harmonic oscillator like a classical harmonic oscillator, because you put there and you'll find this wave packet is moving back and forth at the frequency, which is equal to the harmonic oscillator frequency. And for the coherent spin state, we can find equivalent operator. We define S plus and S minus. So Sx can be decomposed to these two, and Sy the same thing. And S plus and S minus they are equivalent to the creation and the annihilation operators. And just do something similar again. So we talk about the ground state. Equivalent ground state for a spin system is when the spin is pointing along the z direction. When we tip the spin a little bit off from the z axis, and it starts precessing, and the precession frequency is similar to the oscillation frequency for a simple harmonic oscillator. The uncertainty, because the difference between this case and the conventional simple harmonic oscillator is because the commutation relation we know, the uncertainty product of x and p is just equal to h, over 2. But for this one, it's actually equal to the amplitude of the spin over 2. And therefore, the uncertainty is going to be proportional to square root of n. And that means when we add more spin particles into the system, and the uncertainty is getting larger and larger. Okay, then quantum 2.0. So my definition of quantum 2.0 is actually if you can make the quantum sensing with the precision or sensitivity better than the standard quantum limit, then that's what I mean quantum 2.0. And in order to achieve that, we have to use non-classical quantum state, meaning not the coherent quantum state. You have to use some other kind of state, for example, squeeze spin state for spin systems. And typically, again, if you look at the test book, when they talk about, okay, how you generate the squeeze state is you just apply a squeeze operator, right? And then you have a squeeze state. But in reality, how are we going to do this? That really depends. But the point I want to show here is when you look at this, what's important is you see either the square of annihilation operator or the square of creation operator. What it does is really generate something like what we call the two quanta interaction. I'll explain later. But for example, for the simple harmonic oscillator, to make an amplitude squeeze state, it's actually pretty straightforward. You adiabatically ramp your potential, make it narrower and narrower, right? So it kind of folds the distribution getting closer, narrower and narrower too. And then you suddenly change it back, and that's a squeeze state. This one has smaller uncertainty in space. And that's why we'll do, by applying something like this. The point is that you need to generate some kind of interaction which has the quantity or the interaction which depends on a specific quantity square. For example, for this one, it's basically just a position operator square. And by doing this, you can generate the amplitude squeeze state. For spin, the same concept. What we have to do is we have to generate some kind of interaction Hamiltonian, which can give us Sx squared or Sy squared or whatever. You will find the equivalent squeezing operator, which is involved with S plus squared and S minus squared there. But since we know Sx squared will give you some terms like S plus squared and S minus squared, this interaction will also give us a squeeze state. And to try to give us more like intuitive picture, what we would do is if we look at the block sphere again, and then we have a spin pointing to a z direction. Now the z is actually in and out of the screen, and x is actually the north pole here in this case, and this is y. This is minus y. When we apply an interaction Hamiltonian like Sx squared, what it's going to do is, because we know Sx means like it generates a rotation about x-axis. And if we only have a term which is proportional to Sx, this entire sphere rotates along one direction because it's only linearly proportional to the Sx operator. But if the interaction Hamiltonian has actually a term like Sx squared, the northern hemisphere and the southern hemisphere, they actually turn into the opposite direction, right? Because of the square term, it's like taking the absolute value. It doesn't change the sign. So let me come back. The upper and the lower hemisphere, they actually rotate opposite direction, and this kind of shearing force change the original spin distribution into this shape. And this is the very famous or the so-called one-axis twisting idea. By doing this, we will see that's a direction of the spin vector which give you smaller uncertainty. In this case, it's somewhere along this direction. All right. And later you can always try to make, rotate this sphere, for example, just rotate about z later and then make this, like say, on the yz plane, and then you will have a minimum uncertainty along the x direction. Or you can rotate the other way, so we have minimum uncertainty along the y direction. So either way, the point for this slide is regardless which approach or implementation we try to generate or produce squeeze state, for spins or simple harmonic oscillator or photons, what's important is we need interaction which is not linear, or in other words, non-linear. So at least a square term there, and that's how we're going to do this. So for example, when Chad was talking about how to generate the squeeze amplitude state using a nonlinear medium which has index of refraction, depends on the electric field amplitude or photon numbers. It's similar to this kind of things. This is something like if we have a larger x amplitude, it will rotate faster. If it's smaller, it rotates slower. So that's how we actually, distort the original symmetric distribution into this cigar-shaped like distribution. And once it turns into this kind of distribution, we can always try to perform different kind of manipulation to take advantage of the along some direction on the phase, plane or in the phase space or on this block sphere to find the smallest uncertainty, and we can take advantage of that. Another quantity I want to introduce is the squeezing parameter, and for the spin system it's defined like this. And you can see if for the standard quantum limit, this squeezing parameter is equal to 1 because Sz is proportional to n, number of particles, and sigma x is proportional to square root of n, and this factor of 2 there, just try to make it 1. So when it's in the standard quantum limit, no squeeze state, this spin coherent state, the numerator and denominator, they are both 1, and then we can have the 1. But if we use spin squeezing, sigma x can get very small. And actually, the smallest number is just a single spin particle uncertainty, and which is 1/2. And for that, you will see this zeta, the spin squeezing parameter is equal to 1/n. And this is the so-called Heisenberg limit. Okay, so classical limit, we get uncertainty, which is equal to 1/square root of n. And for Heisenberg limit, is 1/n. So we have a square root of n better improvement in terms of the measurement uncertainty. And this final highlighted one, just I want to point out, 2 quanta interaction Hamiltonian is how we are going to generate squeeze state. And this one, just a little bit more about the spin squeeze state. Just try to get more insight in what it actually looks like. Here we just assume we have 200 spin particles, okay? And 200 spin particles, we know the maximum and minimum angular momentum is equal to 100 h bar and minus 100 h bar for a spin 1/2 particle. When the spin is pointing to along the z direction, and we see the uncertainty along x and y, you can find the distribution looks like that. And it's pretty close to a Gaussian, because after all, we have a discrete spin state here. It's not really like continuous, spatial distribution like a simple harmonic oscillator. And then you find this is what we usually call the spin coherent state. When we generate the squeeze state, so one quadrature gets much narrower and the other one gets much broader. So when we try to do the measurement, we can take the advantage along this direction instead of the other one, right? So for example, we want to measure the phase along the x direction, and then we'll get much better or much smaller uncertainty. But the y uncertainty gets much bigger. But this is not the whole story, because when we only look at x and y, that's just a projection along these two directions. In reality, we do know this is a spin in the 3-dimensional space, and we do have a one projection along z. And what it looks like if we zoom in, so if you look at these 2 panels, for the spin coherent state, and we have 100% polarization, so all the spin particles are pointing to z direction, positive z. For the squeeze state, we actually have to sacrifice the purity of the spin projection along z. And not just that, we'll see it actually occupies every other angular momentum quantum number. So the maximum is 100, right? And then 99 is missing, and 98, and then 96 is missing. And that's because, as I mentioned before, the 2 quanta of transition is important for generating squeeze state. So it doesn't occupy in between. And that's kind of one of the example of that. All right. Okay, then talk about the metrological improvement using a squeeze state. Most of the time people think, okay, once we are able to squeeze the spins, we should gain a lot because we can get this improvement factor of square root of n. But in reality, especially for vapor cell system, even non-vapor cell system, like all the atomic systems, we do know the spin state doesn't have infinitely long coherence time, which means, due to many reasons, uh, the, the, the decoherence exists or the decaying of the state exists. And therefore, we know for performing the measurement, we want to make sure, to maximize the sensitivity. Usually, we want to take advantage of the longest coherence time. And in this case, that's a quantity T2 here. So that's what we usually define, how long the coherence can exist. Spin squeezing actually doesn't help at all if your measurement time is longer than T2. And I'll try to explain this quickly. So what happened is, as long as a system has a finite coherence time or finite lifetime, due to other reasons, for example, spontaneous decay, collisions between spin particles, they will all cause decoherence or spin realization. When that happens, it destroys the original state. For spin coherent state, it's basically just like a classical sum. You just add the contribution of each individual spin together for the total measurement precision. For spin squeeze state, it's what we call the highly entangled multi-particle state. In other words, like a superposition state of multi-particle. That it becomes more sensitive to the spin decay or decoherent mechanism, because any decay, like due to the collision or due to spontaneous decay occur, it basically destroys the entire superposition state of the multi-particle system. And therefore, when we generate the maximum spin squeeze state, the effective decay rate also scale with the same number. And what it means is, if we try to measure the signal beyond the longest coherence time, we cannot actually effectively produce spin squeeze state because it quickly gets destroyed. If we say, okay, we try to perform the measurement shorter than T2, we can preserve the spin squeeze state for some period of time and perform the measurement, and then we will gain the advantage of that improvement. So spin squeezing in general, it can give you a broader detection bandwidth, but it doesn't ultimately improve the detection sensitivity if our measurement time is beyond the longest coherence time. So let me put it this way. So this figure, this plot is basically saying, okay, T2 is kind of the boundary. If we try to get a faster measurement, meaning like broader bandwidth, we can take advantage of spin squeezing, and this is the amount that we can acquire. Beyond T2, basically, it will be the same because you cannot effectively generate spin squeezing because it will get destroyed quickly by any decaying or decoherence mechanism. All right. Okay, then the challenge of non-classical quantum state. Spin squeeze state is just one kind. We know there are several others, like for example, GHZ state or the noon state specifically, for photons, and GHZ is like for multi-spin systems. Non-classical state is great. Either like you can reduce the phase uncertainty greatly, and then you can improve the measurement. Or you can increase the fringe density when you try to do, for example, interferometry. But in practice, what we really care is the final sensitivity, which not only determined by the uncertainty of the phase measurement or the density of the fringes, it is also determined by the signal-to-noise ratio, right? So the real figure of merit is a signal-to-noise ratio over the uncertainty of your measurement or the fringe density, or times the fringe density, the other way. But so look at this. So this is the work published a while ago, and it demonstrates, yeah, we can generate the noon state, to give us a fringe density 4 times denser than the classical light. But if you look at the vertical scale, the photon count, from, I cannot read, like 150,000 and all the way down to 0.05. So even though we improve the fringe density by factor of 4, but we lose SNR by factor of 200, overall, the sensing performance is still reduced by factor of 500, which means it's worse. So that's the main challenging of using the non-classical quantum state, or my definition is the quantum 2.0, to really bring the benefit for specific measurement. But anyway, I don't want to downplay the quantum 2.0 sensing, because it does have lots of advantage. It's just we have to find right measurement circumstance or condition for that. So it really depends on what kind of measurement criteria or constraint we have. So quantum 1.0, in my definition, is as long as the sensing application, the sensitivity is dominated by standard quantum limit, and that's what I meant by quantum 1.0. This is usually often the easiest approach, because you don't need to try very hard to generate non-classical or the entangled state between multiple spin particles, and you just need to keep adding more spin particle to improve your sensitivity, because we know that's a scaling factor which is equal to square root of n, and by keep doing that, you will get better result. But there are scenarios you cannot just keep adding more particles, because it may end up in the way like you just keep adding more particles, for example, like more photons, and then the intensity getting too strong, you may just destroy your detection target or introducing some adverse effect, for example, LIGO. That's a very nice example of why this quantum 2.0 approach is useful, because by adding more light, it actually affects the stability of the mirrors using LIGO. Or you think about some other scenario, like you want to probe live cells like in vivo, and then you cannot keep dumping the optical power to that, because you can kill the cell. So some scenario like that say, okay, we do have a constraint restriction. We have to limit our use of number of particles. Then we have to go through the quantum 2.0 approach, because we cannot just keep adding number of particles, like spins or atoms in this case. But in reality, I would say 90% of the time, you just keep doing that, and you always get better sensitivity. And so you don't need to try super hard, to generate non-classical quantum states. Okay, so far that's kind of a quick overview of the atomic metrology in terms of quantum 1.0 and quantum 2.0 approach. Now I'm really going to the vapor cell physics. Okay, so vapor cell means, we basically just, I'll talk about it next slide. But the atomic spaces we use in vapor cells, they are basically the elements on the first column of periodic table. And I mean, we know, basically the reason we would like to do that is because it's hydrogen-like. It has only one valence electron, just like hydrogen. The inner shells are filled, and so we only have one electron in the s orbital. And most of the time, people use like from lithium, sodium, potassium, rubidium, cesium. And here I only list 3 atoms, from potassium to cesium, because there's another advantage is their vapor density or vapor pressure is high at the room temperature, meaning you can get lots of atoms even without heating them up, because their melting points are low and their vapor density is high, even at the room temperature. We can easily achieve 10 to the 12, 1 trillion atom per cubic centimeter, and that's lots of atoms for us to use, and that's the major advantage. And because the simple electron orbital structure, just one valence electron in s orbital, the optical interrogation schemes are also easier. And usually we talk about the 2 major transitions, D1 and D2 line. And these 2 transitions are actually originally from sodium spectrum. They see those bright 2 yellow lines there and name them D1, D2, and then we later just say, oh, okay, we call all this corresponding transition D1 and D2. Okay, so the major advantage of vapor cell is we don't, compared to other atomic systems, we don't need to make a complex scheme for trapping the atoms or ions, and we don't need ultra high vacuum chambers. Atoms are physically trapped by a physical container, which is a glass vessel here. So we don't need a laser beam to trap atoms. We don't need to cool them down. We just place alkaline metal inside the glass cell, and at room temperature, or heat it up a little bit, and we get lots of atoms in there. Okay, so that's a major advantage. And this advantage gives us a better way to make field deployable atomic sensor devices, because you can reduce the burden of making laser trapping or ion trapping or and cooling other mechanisms. So that's the bullet here. This simplicity enables low swap. So swap stands for size, weight, and power, and you can make portable atomic sensors. Okay, then let's compare the performance using vapor cells. The clock, currently the best demonstrated number is 10 to the minus 13, which can integrate down to 10 to the minus 15. Of course, compared to the state of the art, 10 to the minus 18 to 20, this is definitely a few order of magnitude worse. But with this kind of stability, there's still very broad application space, especially, for example, the GPS system we've been using a lot these days. We use atomic clock based on vapor cell in the satellites orbiting around the Earth with this kind of precision level. So that's already pretty good. For magnetometer, this is actually the best. 10 to the minus 16 is the same number I quoted in the previous slide. Accelerometer is much worse, right? I think the best number using atom with the cold atoms is 10 to the minus 11, and this is 10 to the minus 4. The MMR gyro 10 to the minus 3 compared to 10 to the minus 6, the state-of-the-art atomic gyro is also 3 orders of magnitude worse. Then the electric field, this is also the best value. So vapor cells, not all of them can deliver the best performance in terms of the measurement precision or sensitivity, but at least for magnetic field and electric field, we actually don't need to cool the atom down to a very low temperature if we only care about sensitivity, and if we also don't have some other constraint like, say, the size, the spatial resolution or some other thing, if you want to generate the non-classical quantum state. And vapor cell can do a pretty good job. All right. Okay, for the vapor cell, what we have to do is not only just fill alkaline metal into the glass container, we also have to put buffer gas into the vapor cell. And that's because we want to prevent the atoms from colliding with cell wall. By adding buffer gas, the motion of the atom inside the vapor cell will turn from a ballistic motion, like just running along the straight line and hitting the cell wall, to diffusion mode, because atoms, alkaline metal atom will collide with buffer gas atoms, and throughout the collision, instead of like straight line motion, it becomes like multiple collision and ended up like a diffusion motion inside the vapor cell. And that can greatly reduce the decoherence or spinnerization due to the collision between the atom and the cell wall. So if you look at the line width, for example, here, these two plots illustrate two examples using argon and nitrogen as buffer gases as a function of the gas pressure. And we also include like all different spinnerization mechanisms here for different lines. The ray curve is the sum up, the total spinnerization speed. And we can see there's a minimum point by adding the buffer gas. We can reduce the spinnerization or the decoherence rate to some minimum value, and keep adding more gas, the collision-induced spinnerization can dominate the decoherence. So that's an optimal point, for the buffer gas pressure. This is one of the reasons why we want to add the buffer gas. The other one is what we call try to provide quenching mechanism. So when we, the way we access internal quantum states of atom is through most of the time through laser beams or optical fields, and that means we always, every once in a while, we excite the atom into the excited state. And for atom to be useful again, they have to come back to the ground state so we can continue to access them. This excitation mechanism can happen through two different ways. One is through spontaneous decay. The problem with spontaneous decay is it emits photon, and that photon can be reabsorbed by nearby atoms. And that causes the issue what we call the radiation trapping. So photons got re-emitted from the atoms, from the excited atom, and then be absorbed by the nearby atom. And then that nearby atom will get excited again. And this is actually the major mechanism which cause a depumping or depolarizing effect, meaning like when we try to polarize the atom, or do some kind of state preparation for the atom, this radiation trapping will destroy that. And that's a kind of bad thing. And that depends on what kind of buffer gas species we use. For argon, it actually doesn't help with mitigating the radiation trapping because collision between argon and the excited alkaline atom will cause spinnerization in the excited state, but it doesn't help with de-excite the atom back to the ground state. But if we choose nitrogen, so the difference between argon and nitrogen, apparently this is a diatomic molecule, and this is just a monatomic particle. The diatomic molecule has more internal energy state because it has a vibrational and a rotational state. Those states can actually absorb the energy of the excited atom and bring the atom back to the ground state without re-emitting photons. And using nitrogen can mitigate the problem of radiation trapping. And here's the picture of that. If you grab a vapor cell and then you just shine a near IR beam, which you cannot see, from this picture, and you see, and this one is actually a rubidium cell. You start seeing this purple color beam inside the vapor cell, and this cannot be due to near IR, right? Because near IR photon, we can't see that. This is something like close to the blue and violet color. And the reason of this is because the radiation trapping. Excited atom emit photons, get reabsorbed by nearby atom, and while this atomic vapor keeps doing that, atoms will get excited even into the higher lying state, and when they decay back to the ground state, you see the high energy photon. And this is the sign of radiation trapping, which cause the depumping and also the depolarization of the, when I say depolarization, means I destroy the spin polarization of the atom. And that's the effect we don't want to have. Okay, now let's jump to some physics about the atomic vapor cell. So the nice thing about the atomic vapor cell, like I mentioned before, is it's pretty easy to play with. You don't need to trap the atom using a complicated laser scheme. You don't need to cool the atoms, from hundreds of microkelvin down to nanokelvin. That's a pretty significant process, for cold atom, ultra cold atom systems. Vapor cell, we just put atom inside a glass container and add buffer gas. But the physics is actually complex because of the existence of buffer gas. And usually the way we treat a vapor cell atomic system is through a density metric formalism. And I don't need to go through the detail, but basically what I want to point out is we can formulate a density matrix to describe atomic vapor cell system and to see how they evolve over time and what kind of realization mechanism is causing like different decoherence phenomena. And anyway, the point is we have to generate a unitary operator for a collisional process, and then throughout this math, you can derive this spin realization equation. It's usually called the Lindblad form, but you can actually derive this, from the unitary operator. And if you combine like all other terms, you can find the fundamental Hamiltonian and the interaction Hamiltonian to give us the time dependence, and also the spin, the dissipation term, because this is not a closed quantum system; it's an open quantum system. Okay, I want to quickly go through like different collisional mechanisms. One is called the spin rotation interaction, or S-damping. So what happens is, if we have an alkyl metal atom, in this case, like a rubidium, it collides with a buffer gas atom, helium here, and when they close to each other, the atomic spin actually coupled to the angular momentum of the two colliding particles. And when that happens, it will move the population randomly, from one quantum state or the atomic sublevel, to another. And after a few times of this kind of thing happen, eventually it will completely destroy the spin polarization or the prepared state in the atom. And the mathematical forms like that. And here, to give you a quick example, you can actually solve this to see there are several eigen decay modes, for rubidium-87 ground state sublevels. And each mode has its own decay rate. The other one is what we call the hyperfine shift interaction. Again, the collision between the alkyl metal atom and the buffer gas particle can cause the random modulation of the energy level splitting between the associated energy levels. And when that occurs, you look at it in time domain, it's equivalent to the coherence decay. And the mass, form for density metric formalism is here. And we have very important mechanism called the spin exchange. This alkyl metal atom with one electron, valence electron, can get polarized. When they collide with each other, they can exchange their spin. And this is actually a very important mechanism for many applications. How we polarize one species and transfer the spin polarization to another, or even from electron spin to nuclear spin. And this is between atomic species. We can polarize alkyl metal atoms and then get transferred to the nuclear spin of the buffer gas atom. In this case, it's going to be helium-3. Helium-4 doesn't have a nuclear spin, or xenon-129 or xenon-131. And that's even more complicated. The collision can occur with three-body collision. And this will actually generate a short-life van der Waals molecule between alkyl metal atoms and noble gas atom. The reason I put it here, because this also has very important application, how we can generate hyperpolarized noble gases, like helium-3, xenon, and others, on the last column of the periodic table. And those hyperpolarized noble gases can have different application. For example, in the neutron experiment, and also the medical diagnostics. Okay, and then this is the diffusion. I talked about the diffusion and the collision with the world. So we add the buffer gas, but we still want to know how fast, how soon the atom will get collided with the cell wall. And once they collide with the cell wall, it completely destroys the coherence and the spin polarization. And so that's something we also have to consider. And in reality, because most of the time the laser beam does not illuminate the entire cell, so the real boundary, or kind of like the virtual cell wall, is actually the edge of the laser beam. because once the atom moves outside the laser beam volume, we basically lose the signal from that, and it's equivalent, it completely destroys the spin polarization. So far we've been talking about the ground state, spin realization or decoherence mechanism, and then also the excited state realization mechanism as well. One thing I really mentioned is the quenching mechanism. When excited atom get collided with a buffer gas particle, it will get excited back to ground state without re-emitting photons. And that can introduce some kind of spin realization as well. The other one is it gets collided, but it only introduces redistribution of the excited state sublabel, but it doesn't de-excite the atom back to the ground state. And these two actually make very different phenomena and affect the performance of the vapor cell sensor. Okay, then the final one is the optical pumping. We use optical fields to interrogate the atomic states and also to do the state preparation. And like I mentioned before, for alkaline metal atoms, usually we only need to pay attention to the two major transitions, D1 and D2 transition. So D1 is the transition from the ground state, S1 half, to the first excited state, P1 half. And that's a fine structure splitting between P1 half and P3 half. That's the transition. So from ground state to the P3 half, that's the transition, the so-called D2 transition. And using these two, we can basically manipulate the state population or do any kind of state preparation, and also interrogate the signal. Again, for the density matrix formalism, it's written here, but I don't think I want to get into that. The point is, photons can cause random photon scattering, but can also introduce odors into the internal atomic states. And that's what we call the optical pumping or the state preparation. Okay, in summary of the density matrix formalism for vapor cell physics, it's written here. It contains all different terms due to different collisional or photon scattering mechanisms. And the nice thing about the vapor cell is you just have a glass container with alkaline metal atoms in there and some buffer gas in there. You can do all different kinds of things. Like I mentioned, the 5 major categories of atomic metrology can be realized with the same approach. And what you have to do, just you shine laser beam through it, you maybe illuminate the cell with a microwave or RF, apply bias magnetic field or electric field. You can look at the transmission of the laser beams at different wavelengths, or look at the fluorescence, or even look at the radiation from the atoms in the microwave and RF frequency bands. And that's the way how we do sensing application for different physical quantities with vapor cells. And it's way simple compared to co-atom systems. All right. Just for your information, if you are interested, I would recommend, in terms of the detail of the vapor cell physics, you can look at this paper published in 1972, I think. This is published in Review of Modern Physics, or this book. So they talk about how we actually calculate the complex atomic system, like a vapor cell. Okay, so far that's the topic from introducing the atomic metrology and then going to the vapor cell atomic physics. If you have any questions, please let me know. All right, if not, I'll move forward. Or do we want to take a break? Or?
Time for a break at some point. It's when
Mm-hmm.
this is a good time.
Yeah, I can't. So I think after this, I'll talk about 3 examples in terms of the innovation of vapor cell-based atomic sensors.
Okay.
Yeah.
let's take a quick 15 then, and then we'll come back for the 3 different innovations in that. So.